Today's lesson, we're going to be looking at solving exponential and logarithmic equations and a lot of different varieties of both of those. We'll then be able to use those for our following lesson on using them to solve applications of exponential and logarithmic functions. So first, looking at logarithmic equations, if we have the following, log base b of m is equal to log base b of n, then m must equal n. Notice in this equation, the bases of both logarithms are the same. That must mean that our arguments are equal. So we'll use this to solve a few examples, but what we want to remember when we're solving a log equation is that we must always check our solutions in the original problem. And that's because of the restrictions on the domain of a logarithmic function. Remember that we can't take the logarithm of anything less than or equal to 0, so it must be positive. So we got to make sure that when we plug our answers back into our original problem that our arguments are positive. Log base 4 of x plus 2 equals log base 4 of 8. I notice here that the bases of both of my logarithms are the same, so that means that my arguments must be equal. X plus 2 equals 8. And this is a nice baby equation, easy to solve by subtracting 2 from both sides. X equals 6. Now again, before I commit to that answer, I need to plug it back in. This isn't an optional suggested check. This is a required check because a log equation can produce extraneous solutions. So I'm going to check my answer. Log base 4 of 6 plus 2 equals log base 4 of 8. And I can simplify inside the parentheses. I see that log base 4 of 8 is equal to log base 4 of 8. Now, in this example, it's very clear to see that the left side is equal to the right side. But what you really want to make sure that you're paying attention to is that whatever the arguments are positive. That's going to be the key in making sure that these work. It's not so much that the left side is equal to the right side. Hopefully that will be the case. But in our check, we're just making sure that our arguments, the arguments are positive. 2 log base 5 of x equals 3 log base 5 of 4. If you look at both sides of the equation, I don't have just one log equal to another log because they both have coefficients. So the first thing we're going to use are the properties of logarithms to move our coefficients to exponents. This is what we did when we were condensing logarithms in our previous lesson. So we now have log base 5 of x squared equals log base 5 of 4 cubed. And now that our bases are the same, x squared is equal to 4 cubed. 4 cubed is 64. And now to solve this, we take the square root of both sides. When we take the square root, we should be remembering that we always add our plus or minus. So we get two solutions for this equation. We get x equals 8 and negative 8. And now we have to check both of those in the original problem. So if I check x equals 8, plugging that just into my arguments, is 8 greater than 0? Yes. And then on this right-hand side, I don't have an argument involving x. If I check x equals negative 8, when I plug it into this one, can you see where my cursor is? All I'm checking is my argument. Is negative 8 greater than 0? No. So that answer does not work. Our only solution is x equals 8. Now I want you to be very cautious. Don't always assume that when you get two answers, the positive one works and the negative one doesn't. You need to plug them back into each individual argument and make sure that those arguments remain positive when you plug in your solutions. Log base 6 of x plus 4 plus log base 6 of x plus 3 equals 1. Now in this example, we can't use what we used previously where we set two logarithms equal to one another and then we're able to set their arguments equal to one another because we can't isolate both of those logs at the same time. No matter what, even if I condense these two, they're not equal to another log of base 6. So we're going to use a different technique. We're actually going to use exponentials to undo the logarithm. But first we want to condense. These two logarithms that are being added can be condensed using multiplication. So this is log base 6 of x plus 4 times x plus 3 equals 1. And now if you recall from a few lessons ago when we were converting between exponential and logarithmic forms, to convert this to exponential, we start with the base, we raise it to this power, and then we're going to set it equal to our argument. So our new equation looks like 6 to a power of 1, which we don't need to write that, it's still 6, equals x plus 4 times x plus 3. When I'm looking at this and I'm thinking about how to proceed forward to solve, I'm going to want to FOIL out the two binomials and then set it equal to 0 so that I can refactor to find my solutions for x. So we've got x squared plus 3x plus 4x is 7x. 4 times 3 is 12. And we will subtract 6 from both sides to set it equal to 0. Plus 6. And now we can factor this. Factors of positive 6, that sum to positive 7, positive 6, and positive 1. So now we can see our two solutions are x equals negative 6 and negative 1. But we're not done. We have to make sure anytime we start with a logarithmic equation that we plug them back into our argument to make sure that our arguments are positive. So I'm first going to check the solution x equals negative 6, but I have two different arguments. I've got this argument, x plus 4, and another argument, x plus 3. I need to plug that value of negative 6 into both of them, and they both need to be positive. If I plug x equals negative 6 into either of them and they're negative, I cannot evaluate a log of a negative number, so that would not be a solution to our equation. So is negative 6 plus 4 greater than 0? No, it's not. So I don't even really need to check the second one, but I will. Negative 6 plus 3 is also not greater than 0, so that solution is out. Now we check negative 1. Negative 1 plus 4, is that positive? Yes. We check the second argument, negative 1 plus 3 greater than 0. Yes. So our answer is just x equals negative 1. The natural log of x plus 1 minus the natural log of x equals 2. There's that weird box. I'm not sure what it is. But either way, proceeding forward, again, we want to first start by condensing the two logarithms on the left. Since we are subtracting two logarithms, we're going to condense using division. So this is the natural log of x plus 1 over x equals 2. Now, if I want to solve for x by converting to exponential form, I need to remember what my base is. When we have a natural log, the base is e. And if you want to write that in, that's a helpful tool so that it's easier to convert. So we start with our base, raise it to this power, and then set it equal to our argument. So we have e squared equals x plus 1 over x. And now we're trying to solve for x. Notice here e squared, you want to keep in mind that that is just a number. Remember that e is that 2.71828 number, so e squared is, I don't know, probably somewhere around 4 or 5. But it is a value, it is a number. We don't want to treat it like a variable. So I'll multiply both sides by x to clear the denominator. So we have e squared times x equals x plus 1. We want to combine all of our x terms together, so I'm going to subtract x from both sides. E squared times x minus x equals 1. And now I can factor out an x from this side. E squared minus 1. And now we can solve for x by dividing both sides by e squared minus 1. Now, if I look at this, we can use our calculator to approximate that. If we do that, we get approximately, I think it's what, 0.16. And we can use that approximation just to check, but be careful with the directions in your homework or on the test. If it's asking for an exact answer, you want to leave it as 1 over e squared minus 1. Only if they ask you to round will you give a decimal approximation. So coming over here to check, we've got 1 over e squared minus 1 plus 1 greater than 0. Well, if this ratio is about 0.16 and we add 1 to that, it's going to be positive. And then we also have to check our second argument. Remember, we've got 2 of them here. This one and this one. We're going to check our solutions in both arguments. 1 over e squared minus 1 alone greater than 0. Again, since we looked at the decimal approximation and it was 0.16, it is positive. So this is our solution, and we have verified that it is not extraneous. Log base a of x minus 1 minus log base a of x plus 6 equals log base a of x minus 2 minus log base a of x plus 3. We've got a whole lot of logarithms here. We want to condense it so that we are dealing with fewer. On the left-hand side and on the right-hand side, since our logarithms are being subtracted, we're going to condense using division. So we have log base a of x minus 1 over x plus 6 equals log base a of x minus 2 over x plus 3. Now we see that the absence of a known base, so we had a for our base, it didn't actually make any difference because now we've got 2 logarithms with the same base, regardless of what it is, that are equal to one another. So we can set our arguments equal to one another. X minus 1 over x plus 6 equals x plus 2, minus 2. X minus 2 over x plus 3. To solve this equation, 2 fractions equal, we cross multiply. X minus 1 times x plus 3 equals x plus 6 times x minus 2. And now we're getting on the FOIL train. We're going to FOIL the left and the right, and then combine like terms, set it equal to 0. On the left-hand side, we get x squared plus 3x minus 1x is plus 2x. Negative 1 times 3 is negative 3. On the right-hand side, we get x squared. On the outside, we get negative 2x plus 6x is a positive 4x. 6 times negative 2 is negative 12. And now we want to start combining like terms. So I'm going to start with my quadratic term. When I subtract x squared from both sides, we see, voila, they go away. So this isn't going to be a quadratic equation after all. Two x minus 3 equals 4x minus 12. We'll subtract 2x from both sides and also add 12 to both sides at the same time. So we have negative 3 plus 12 is 9. 4x minus 2x is 2x. Divide both sides by 2. X is equal to 9 over 2, which we know as a decimal, that's just 4.5, which might help us when we're checking our solution in our arguments. Since we're checking back in the original problem, we need to make sure that we check all 4 of our arguments. We've got one here, another one here, another one here, another one here. We're always using the original. We're not using anything that we've condensed. 9 over 2 minus 1 is greater than 0. Yes. 9 over 2 plus 6 greater than 0. Yes. 9 over 2 minus 2 greater than 0. Again, 4.5 minus 2 is still going to be positive. 9 over 2 plus 3 greater than 0? Yes. So we have verified that 9 over 2 is not extraneous. So we've seen a couple different types of logarithmic equations. Either we have two logs that are equal to one another with the same base, and then we can set our arguments equal to one another, or we have to condense and then convert to exponential form in order to solve. Next, we'll look at exponential equations and their different varieties. First, if we've got a to the m equals a to the n, both of our exponential terms have the same base. That means their exponents must be equal. Now, with an exponential equation different than a logarithmic equation, we do not need to check our solutions because we're not going to end up with any extraneous solutions. There are no restrictions on the domain of an exponential function. So we're first looking at that rule, the a to the m equals a to the n. Using this example, 5 raised to the power of 3x minus 6 equals 125. What we want to do is rewrite it so that the bases on the left and the right are the same. 5 raised to the power of 3x minus 6 equals 125. Is there a way that we can write 125 as an exponential expression with a base of 5? And we can. It's 5 to the third power. Again, I can exchange 125 with 5 cubed because 5 cubed is 125. And now that we have our bases the same, our exponents must be equal. 3x minus 6 equals 3. X equals 9, dividing both sides by 3, we get x equals 3. Again, at the end of an exponential equation, you can plug it back in to check, and that's always recommended just to make sure that we have the right answer, but it's not required in these problems because we don't have the chance of getting an extraneous solution. 8 to the power of x plus 2 equals 4 to the power of x minus 3. Looking at these two, can we rewrite them so that they have the same base? Now, I want you to be really careful. A lot of times we look at the 4 and the 8 and we think, okay, well, 8 is 4 times 2, so that's what we're going to rewrite it as. But it's not a multiplication that we're trying to rewrite it as. We're trying to write it as an exponential expression. 4 squared is not 8. 4 squared is 16. So our base is not going to be 4. But is there another base that we can use for both 4 and 8? And that is 2. 8 is 2 cubed raised to a power of x plus 2. And 4 is 2 squared raised to a power of x minus 3. Now notice how I rewrote it. I exchanged or substituted 8 with 2 cubed, but I kept it in parentheses. Same with the 4. And there's a reason for that. If we recall our properties of exponents, when I've got power to a power, I have to multiply those exponents. So I'm even going to throw some parentheses around our exponents so that we remember to distribute here and here. So this equation is the same as 2 to the 3x plus 6 equals 2 to the 2x minus 6. Now we have two exponential expressions with the same base equal to one another. So their exponents, 3x plus 6, are equal. Equals 2x minus 6. We start solving, combining our variables, subtract 2x from both sides. We'll also subtract 6 from both sides at the same time. 3x minus 2x is x equals negative 6 minus 6 is negative 12. When you guys are solving exponential equations, always check first to see if you can get the bases the same, because then we can ignore that exponential altogether and just set our arguments or our exponents equal to one another. E to the power of x squared equals e to the 3x times 1 over e squared. Looking at this equation, is there any term that looks a little off? This last one, because it's a fraction. is there a way to rewrite this last term so that it's no longer a fraction? And yeah, we can. If I wanted to take this e squared out of the denominator, I can do that by making the exponent negative. Now, in previous courses and maybe even in previous examples, we've seen that we don't want to leave a negative exponent in an answer, but in this case, we want to do that so that we can start combining some of these terms. So this is e to the x squared equals e to the 3x times e to the negative 2. Now on the right-hand side, e to the 3x times e raised to the power negative 2. Since these terms are being multiplied, we add their bases. So we have e to the x squared equals e to the 3x. Adding a negative is the same as subtraction, 3x minus 2. Now we have two exponential expressions with the same base equal, so we can set their exponents equal to one another. X squared equals 3x minus 2. This is a quadratic. We want to set it equal to 0 and try to factor. So I'm going to subtract 3x and add 2 to both sides. And the reason I moved these two terms over instead of just the 1x squared is because I always want my lead coefficient when I'm factoring to be positive. All right, so factors of positive 2 that sum to negative 3. It's going to be negative 2 and negative 1. So we see that x is equal to 2 and positive 1. In the last three examples, we saw problems that we were able to make all of the bases the same. But what if you cannot make the bases the same? Just like in the logarithmic problems, we started by having two logs that were equal to one another, so we set the arguments equal. Well, when we couldn't do that, then we used its inverse. The inverse of our logarithm was the exponential, and that's why we converted to exponential form when we started with a logarithmic equation. If we start with an exponential, what are we going to use to undo that? We're going to use logarithms. So looking at a very basic example, we've got 4 to the x minus 15 equals 0. We always want to start by isolating that exponential term. This is our exponential term, the base and the exponent, so we're going to add 15 to both sides. So we have 4 to the x equals 15. And at this point, we could still check, is there any way to get the bases the same? As I had mentioned before, if you can, it makes it so much easier to get to your answer. But in this case, 4 and 15, there's no common base, so we're going to have to use something different. Our next step is to undo that exponential by taking the natural log. Whatever we do to one side, we have to do the other side, don't forget. And this can also be done using our base 10 logarithm, and we will see that in one of our examples coming up. I typically just always use natural log, but that's just from my training and my experiences. I've had teachers that have always used natural log. In this video, we will see both applications, and we'll even talk about when you might want to use one over the other. So if I take the natural log of both sides, this looks like the natural log of 4 to the x equals the natural log of 15. So now looking at that same equation, natural log of 4 to the x equals the natural log of 15. Now we're going to start using those properties of logarithms to rewrite this so that we can solve. The property that we're going to use is that power rule. What that says is we can take the exponent of our argument and bring it out front as a coefficient. So we've got x times the natural log of 4 equals the natural log of 15. To solve for x, divide by the natural log of 4. So we get x equals the natural log of 15 divided by the natural log of 4. When we're solving these types of problems, we're going to end up with a lot of answers that are in terms of a natural log or a logarithm. Make sure that you guys remind yourself that the natural log of 15, the natural log of 4 are numbers. Just like 15 and 4 are numbers. Having that natural log out front doesn't mean that it's a variable. We want to make sure that we keep that in mind. The only variable is that x or y or z or whatever the variable is in the problem. Also, the natural log of 15 divided by the natural log of 4 is not the same as the natural log of 15 over 4. It's not the same thing. If you want to prove it to yourself, plug both of these expressions into your calculator. You'll see that you don't get the same answer. Five to the x equals 134. In this example, we'll try using a base 10 logarithm just to see that it works. Now we have our exponential term already isolated, so we don't need to move anything. And 5 and 134, hopefully it's pretty obvious we're not going to be able to get the same base. So we're going to go straight to using our logarithm. We're going to take the log of both sides. And then we're going to use our properties of logarithms to rewrite this. In particular, we're using that power rule. So we've got x times log of 5 equals log of 134. And to solve for x, we just divide both sides by log of 5. Now, I want you guys to try plugging this into your calculator in the event that the question is asking you to give an approximation of your solution. Go ahead and plug this into your calculator. Be very careful though. In many calculators, you need to add extra parentheses. So go ahead and try this. And you should end up getting 3.043. If you're not getting that decimal, it just has to do with the way you're typing it into your calculator. You can always bring your calculator by my office or to class and we can take a look at it, make sure that you know how to type stuff in, make sure we're not missing any parentheses. The difference, the first is our exact answer, the decimal is our approximation. So we've applied both the natural log and log base 10 to undo our exponentials. Now let's talk about when we might want to use one over the other. If we're looking at this example, we want to solve 10 to the x equals 8,000. Do you think we want to use log base 10 or a natural log which has base e? Now, just a side note, you can use either. You will get the same answer, but one might be a little bit easier and a little bit more straightforward than the other. The base of my exponential is 10. So the inverse of an exponential of base 10 is log base 10. So we're going to use that. So log of 10 to the x equals log of 8,000. And the reason why we wanted to use our base 10 logarithm is look at this expression. Do we recognize this as one of our properties of logarithms? Hopefully, we recognize this as our inverse property of logarithms. I'm going to shoot over here just to write that out. Remember when we had log base b of b to the x? What did that expression simplify to? It simplifies to x. This is the same thing that we have here. We have a base of 10 in our logarithm, a base of 10 in our exponential, so it's equal to that exponent x. So this whole expression is just equal to x, and that is equal to log of 8,000. You would end up getting an equivalent answer using natural logs, though. It just wouldn't look the same. 7e to the 2x minus 5 equals 58. Again, the first thing you always want to do is make sure you isolate that exponential expression. So here we've got some work to do. This is our exponential expression. We want to undo everything else. So we're going to start by adding 5 to both sides. 58 plus 5 is 63. And then dividing both sides by 7. So we have e to the 2x equals 9. And here I'm going to ask that same question. Do you think in this particular example we'd be better off using natural log or log base 10? Well, in the last example we used log base 10 because the base of my exponential term was 10. Here the base of my exponential term is e. Natural log also has a base e, so they are inverses. So if I take the natural log of both sides, we have the natural log of e to the 2x equals the natural log of 9. And again, here we see our inverse properties of logarithms. Now, I gave you the list using a log with any base, and also the same exact rules or properties with natural log. But to remind you, over here, we had the natural log of e to the x. That was our inverse property for natural logs, and that is equal to x. If we look at the two problems, we've got our natural log of e to the 2x, so that's what is replacing the x in our rule. Oop, sorry. Hang on, I'll get there. There we go. Sorry about that, guys. So this whole expression is just 2x equals the natural log of 9. To solve for x, we divide both sides by 2. X is equal to the natural log of 9 divided by 2, not the natural log of 9 over 2. Be very careful, guys. We're not pulling numbers that are not part of the argument into the argument and vice versa. I'm going to erase this. This entire natural log is being divided by 2. And we can approximate this using our calculator. We should get the value 1.099. It's really important that we're able to use our calculator. When we start moving into applications, the decimals are going to be a little bit more meaningful to us than having these exact ratios. Three to the 2x minus 1 equals 7 to the x plus 1. If you notice in this problem, we've got our exponential expression isolated, but we have two of them, one on both sides. 3 and 7, we're not going to be able to get the same base, so we're going to have to use logarithms. At this point, neither natural log or log base 10 is going to be the direct inverse of either of these, so we can use either one. This is where I say I always go with the natural log, but it doesn't matter. You would get the same answer using natural log or log base 10. So the natural log of 3 to the 2x minus 1 equals the natural log of 7 to the x plus 1. And now we use those properties of logarithms where we can bring our exponents down as coefficients. But one thing you want to notice is that our exponents are not monomials, they're binomials now. So we're going to have parentheses around them when we throw them in the front as a coefficient. So we have 2x minus 1 times the natural log of 3 equals quantity x plus 1 times the natural log of 7. Now this equation looks funny, and the reason it does is because we've got the natural logs in there. But you have to continue to remind yourself, natural log of 3 and natural log of 7 are just numbers. They're not pretty numbers, they're not integers, but they are in fact real numbers. So we treat them and use them just like we would if it was a 3 or a 7. If this had just been a 3, what would we do with it? We would distribute it into the parentheses. So that's what we're going to do even though it's a natural log of 3. The same thing over here with that natural log of 7. If this had just said 7, we would distribute it. So that's the same thing we'll do when it says natural log of 7. The 2 and the natural log of 3 are the coefficients, so I'm going to keep them together. So we have 2 times the natural log of 3 times x minus 1 times the natural log of 3 is just natural log of 3 equals the natural log of 7 times x plus the natural log of 7. The use of the parentheses here is just to make sure that you can distinguish between the coefficient and the variable. We want to make sure that the x doesn't appear to be attached to the 3 at all. So that's why I'm using those parentheses, just to make sure that it's clear. Now again, we've got like terms here. This term has an x, this term has an x, this term doesn't, this term doesn't. So we want to combine all of our like terms on either side of the equal sign. We want to combine our x terms together and our terms without the x on the other side. So I'm going to move the natural log of 3 to the right and the natural log of 7x to the left. Those ones will cancel out, and I'm going to subtract the natural log of 7x from both sides. These two will cancel out. So on the left, we have our two x terms. 2 natural log of 3 times x minus the natural log of 7 times x. And that will equal the natural log of 7 plus the natural log of 3. On my left-hand side, that's the side with my x's, they both have a factor of x, so we can factor it out. And what are we left with? 2 natural log of 3 minus the natural log of 7. And this equals the natural log of 7 plus the natural log of 3. And now it's clear to solve for x, we're going to divide both sides by this whole thing in the parentheses. Divide both sides by 2 natural log of 3 minus the natural log of 7 on both sides. Now, what I want you guys to do next, I'm going to have you pause the video in just a second. I want you to give me that answer as an approximated decimal. Okay, so I want you to practice typing this very complicated rational expression into your calculator. Okay, so go ahead and hit pause and try to type this in. And then once you have an answer, I want you to press play again, and I'm going to have the answer up here for you guys, and I want to compare. An accurate, or sort of accurate, approximation of this ratio is 12.114. Now, I'd be willing to bet that a lot of us didn't get this answer. And not because we didn't obviously get the right answer for our value of x, but because typing this into our calculator is very, very tedious. So what I want to work on is taking this expression and simplifying it a little bit so that it's easier to type into our calculator, so that if the question was asking for a decimal, we'd be more likely to get the right answer. So I'm going to rewrite that answer. We had the natural log of 7 plus the natural log of 3 over 2 natural log of 3 minus the natural log of 7. I'm going to erase all this other stuff down here. So let's look at the numerator. If I've got just the natural log of 7 plus the natural log of 3, is there a way that I can simplify those two terms? Now, simplifying means have fewer terms. So in other words, can we condense the numerator? Since our two logarithms are being added, we can condense them using multiplication. This is the natural log of 7 times 3. Now in the denominator, I'm going to simplify more as I go, but just going through one rule at a time. In the denominator, we see the minus here, don't we? But before we can condense this subtraction, we need to condense our coefficients. We need to make sure that we make our coefficients exponents. So this is the same as the natural log of 3 squared minus the natural log of 7. So we'll stop here. We'll simplify what we've got. We've got the natural log of 21 divided by the natural log of 9 minus the natural log of 7. Already this is so much easier to type into our calculator, but we can go even further by simplifying the denominator. The natural log of 9 minus the natural log of 7 can be condensed using division. So this is the natural log of 21 divided by the natural log of 9 over 7, which, although we still have some fractions inside of fractions, believe it or not, this expression, this fraction is much easier to type into your calculator. So go ahead and type it in, and again, make sure that you get that 12.114 approximation for that value of x. And before I flip to the next example, and I want you guys to wait just a second, I'm going to give you guys a task. I want you to look at that example that's coming up next, and I want you to say out loud at your desk, wherever you're at, the first thing that comes to mind. What's the first thing you think of when you look at the equation that we're about to solve? Okay? Hopefully, many of you guys said quadratic, because we've got 3 terms, we've got some like squared term, we got a 2 in there, we got a constant that has no variables, it's set equal to 0. There's a lot of characteristics about this equation that make us at first glance think quadratic. And there's a reason for that. We're actually going to solve this just like a quadratic equation. And we're going to do that using a method called U substitution. U substitution is a method for very basic U substitution is basically where we can take a complicated problem and make it look a little bit more basic. It's used a lot in calculus classes because we're dealing with integrating and differentiating very complicated expressions. But if we can simplify it and make it look a little bit easier, it doesn't seem so overwhelming. So what we're going to do for U substitution, we're going to let U equal the linear term or the middle term without its coefficient. I'm going to put linear in parentheses because that's specifically when we're talking about a quadratic, but it's okay. So our middle term is negative 4e to the x, and we're going to let u equal that minus the coefficient. So the coefficient is the negative 4, so u is going to equal just e to the x. And now what we want to do is rewrite our equation using u instead of e to the x. So we've got e to the 2x. E to the 2x, I'm going to write this over here, is the same as e to the x being squared, because when I've got power to a power, we multiply. We reviewed that earlier. So if e to the x squared and u is e to the x, this first term is u squared. Minus 4 times e to the x is now u, plus 3 equals 0. And now this looks just like a quadratic equation. We're just not using the letter x, we're using the letter u. we're going to factor this. We need factors of positive 3 that sum to negative 4. That's going to be negative 3 and negative 1. So we can see that u is equal to 3 and positive 1. Now, most students think, okay, we're done, yay. But if we look at the original equation, what are we trying to find the value of? We're trying to find the value of x, not u. So we're going to have to go back and back substitute so that we can find the value of x. So we had u was equal to e to the x, and we just solved, we got u is equal to 3 and positive 1. So that means that 3 is equal to e to the x, or 1 is equal to e to the x. And we can solve both of these equations. 3 equals e to the x, we're going to have to take the natural log of both sides. The natural log of 3 equals the natural log of e to the x. Natural log of e to the x, there's your inverse property. This is just x. Over here, the same thing. We have the natural log of 1 equals the natural log of e to the x. Recognizing that inverse property, the natural log of e to the x is equal to x. And what is the natural log of 1? This is another one of those properties that we wrote down a few lessons ago. Now, if you don't have it, you can A, use your calculator to evaluate, or B, let's think about how we evaluate a logarithm. We're trying to find the exponent. So e to what power equals 1? Well, anything raised to this 1 power is going to give you 1. That power is 0. So we have two solutions. X equals the natural log of 3, or x equals 0. So that last example, a little trickier, but again, using that technique of u substitution allowed us to solve just a normal quadratic. The last thing we just had to remember was that we always have to back substitute, and that's where we start integrating those ideas of taking the natural log of both sides to solve our exponential equation. So just to recap, we solved exponential and logarithmic equations. I'll erase that. For a log equation, either we've got two logs equal to one another and then we set our arguments equal, or we're going to convert to exponential form. We always have to make sure that we've condensed first before we convert to exponential form or before we set the arguments equal to one another. With our exponential equations, we first determined whether or not we could make the bases the same. If we can make the bases of our exponential expressions the same, then we get to just set our exponents equal to one another. If we can't make the bases the same, that's when we start undoing the exponential expression by incorporating a log, either a natural log or log base 10. Don't forget when you're solving a log equation that you must check your solutions in the original problem. However, when you're solving an exponential equation, it's not necessary for you to do that. So we'll see you guys next time. We're going to look at applications of these functions, exponential and log functions, and we'll be practicing more solving equations. Have a good one.